So today we're doing experiment 8 for chemistry 120 at Grossmont College, double displacement reactions. So before we get going on all the reactions, I just want to go over again two things. So one, we have just predicting products. So the double displacement reactions involve typical ion exchange. So here I'll color code our reactants. So we've got A and B, and X and Y. Essentially, the cation is always written first. So A was partnered with B. Now it's going to be partnered with Y. So we're going to have AY plus XB. Remember, the cations are always going to be written first, and the anions will be written last. So it's my Y. Just color this in so you can have it as a reference later. Remember, double displacement reactions are kind of three steps. So one, we're going to swap and crisscross. Two, we're going to balance the chemical equation. And then three, we're going to predict phases using solubility rules. The other thing I want to go over are the different evidence of reactions. So here, when we watch the videos for this, we will see a couple different things. If we have clear solutions, essentially, if we have a solid formation, if we have a gas formation, or if we have heat generation, these are all different evidence of reactions. The last thing I'll go over before we get started is there are three products that, if made, will immediately decompose. So what I mean by this is that if you make H2CO3 as part of your double displacement reaction, so this is the product, if it's on the other side, what's actually going to happen is this is going to immediately decompose into H2O liquid and CO2 gas. The next thing can be said for H2SO3. Again, this is if I make this as a product. I'm instead going to write H2O liquid plus SO2 gas. The last one is anything generally with ammonium, but specifically ammonium hydroxide. And this instead is going to be H2O liquid plus NH3 gas. So the first reaction we'll go over is sodium chloride and silver nitrate. So let's write down our observations from the video. So in here you can see that there's already a solution of sodium chloride in a graduated cylinder that was poured from here. So here's a beaker with sodium chloride, and the scientist is now going to add silver nitrate. So you can hear it being poured. And there we go. So you can see here that a white cloudy precipitate has formed. So for our observations, we'll go ahead and write white cloudy precipitate. All right. For the conventional, so this is going to be the traditional molecular equation. We're going to write NaCl, so this is conventional, and I'll be using these colors so you can go back and kind of identify. So these are both aqueous solutions, AgNO3, aqueous. Again, the first thing we're going to have to do is swap and crisscross. So my Ag is going to go with Cl, and my Na is going to go with NO3. So I'm going to have to predict by using my crisscross method. This is Ag plus, Cl minus. Again, Na with the charge of +1, nitrate with a charge of -1, silver with a +1, and chloride ion with a -1. So this is just going to be NaNO3 plus AgCl. So we're going to rewrite this NaCl aqueous plus AgNO3. Aqueous goes to NaNO3, don't know, plus AgCl. The next thing I have to do is balance. So we can see here that there's a 1 and 1, 1 and 1, 1 and 1, 1 and 1. Last thing I have to do is predict the products. We have to figure out which one of these was the actual solid that formed. So we know that Na and NO3, those are both aqueous with everything. And we know that chlorides on the solubility rules tend to be soluble unless they're paired up with silver. So for the total ionic, we're going to split everything up. We're going to split up all aqueous. So this is going to be Na plus aqueous plus Cl minus aqueous. Again, I'm breaking up all of the ions into their individual charges and writing the phase that they're in. This is going to go to, I'm running out of room, so I'm just going to write it below. See, it's going to be NO3 minus aqueous, and I'm not going to split up AgCl solid. Then to write our net ionic, we're just going to write off and basically cross off all spectators. So you can actually do this and cross off the ones that appear, right? Just make sure that I can read it in the lab notebook. Or you can just rewrite it knowing that those are going to get crossed off. So this is Cl minus, AQ plus Ag plus, AQ goes to AgCl, solid. A couple things to note here. It doesn't really matter what order I write those two in, right? What's really important is that the order of the compounds themselves always go cation, anion, but you can write whichever one first. So here I happen to write NaCl first and AgNO3 second. I could have written AgNO3 plus NaCl, or the same thing over here. So let's move on to the second one. So here we've got a solution of sodium chloride and potassium nitrate. So we'll go ahead and watch the video so we can write down our observations. So here you can see there's two test tubes. One has sodium chloride, the other one has KNO3. So we'll go ahead and call that a no reaction. So we'll just write that down on our thing. Remember, the evidence of reaction, it has to be a heat, gas, or solid. So we'll write down just that it had no reaction here. So for the conventional, we're just going to write down NaCl, aqueous, plus KNO3, aqueous. Now remember, the conventional has the compounds together, and it also has their phases, so nothing's split up or anything. So here we're going to have to predict our products. So Na is going to go with NO3, and K is going to go with Cl. So I'll just go ahead and write this down here. And then Cl minus. We have Na plus, NO3 minus. We crisscross these. This just becomes KCl and NaNO3. Now, in this situation, I know they are both aqueous, so I don't really have to do step 3 later. I saw that there was no reaction, so I can go ahead and do that now. This is already balanced, so we're good to go. So I'll go ahead and write the total ionic. Now here's where we're going to split up all aqueous again, remember? So I have to split up everything. So this is going to be Na plus, aqueous plus Cl minus, aqueous plus K plus, aqueous plus NO3 minus, aqueous. This is going to go to K plus, aqueous plus Cl minus, aqueous plus Na plus, aqueous plus NO3 minus, aqueous. Our net ionic, because everything is going to be crossed off, is just no reaction. So you can just write NR for no reaction, or you can actually write out no reaction. So our third reaction is sodium carbonate and hydrochloric acid. So we'll go ahead and write our observations here. So looking at this video. So you can see here in the flask, we have HCl. And in this balloon, the reason that we're using a balloon here will become evident in just a second. And they're putting it on a scale to show you the law of conservation of matter. Anyway, so we've got solid sodium carbonate in this balloon, and we have the liquid hydrochloric acid. So they're going to lift the balloon up into the flask, and we'll see what happens. So here he's going to toss it. You can see it's adhered. So you have the solid. And so here, as this is generating, we see bubbles, right? And the reason that they have the balloon here is that they want to show you that there's gas being produced. So it's a really nice way to show you that. So let's go ahead and write this down. So for our observations, we can write bubbles, you can write gas formation. So for our molecular equation, we're going to go ahead and add these. We also should technically see heat, but it's kind of hard to see in that video, but the main thing is that bubbles and gas were formed. So here, in their video, it was solid, but in our solution, it was aqueous, so you can feel free to write either one. This is going to be plus HCl, and this is going to give me oops, I should partner this up. So this is going to be Na plus and Cl minus. This is going to be H plus and CO3 2 minus. Again, I have my Na and my Cl and my H and my CO3. Something to note here that this 2, I'm not going to bring over. This is different than that 3. That 3 is telling me that that's carbonate. This 2 is here because of the balancing that's required for making ionic compounds. So this is just going to be NaCl, and this is going to be H2CO3. Now remember, I said that when, CO3, I said that when you form this, that you have to immediately decompose it. So we're going to go ahead and rewrite this. So I'm going to say decomposes. So we're going to go Na2CO3, aqueous, plus HCl, aqueous goes to NaCl. I know this is aqueous because of the Na, plus H2O, liquid, plus CO2, gas. What you can do up here is try to balance it, and then you can kind of follow through down here. So I see that there's 2 NAs over on the left, so I'm going to put a 2 here. There are 2 CLs, there's 2 H's, there's 1 CO3. So as long as I bring this 2 down here, the rest of it will be balanced. So the next thing I'll do is write out the total ionic, so split up everything that's aqueous. This 2 is going to come out in front. This is 2 Na plus CO3, 2 minus, aqueous. There was a 2 here too, sorry. So something to note, this 2 is a subscript. It only goes in front of the one that it's behind. However, this 2 is in front, so it goes to both. I'm going to write my down arrow down here. This is going to be 2 Na plus aqueous plus 2 Cl minus, aqueous plus H2O, liquid plus CO2 gas. I'm going to go ahead and write out my net ionic. Feel free to pause this video at any time so you can write down your answers or write down a guess and then check it with what I have written down. So we see that we have the Cl's and the NAs. So this is just going to be CO3, 2 minus, aqueous plus 2H plus, aqueous goes to H2O liquid, and CO2 gas. So the next reaction that we'll do is sodium hydroxide and HCl. And hopefully you guys recognize this as a strong base and a strong acid. So let's write down our observations from here. So we can see here this gentleman has 2 test tubes. One of them has HCl, one of them has NaOH. What you're going to notice is that there is a pH indicator in here. pH indicators can be used to tell you in a visual way the level of acidity or how much H or how much N. So before we watch the reaction, I just kind of want to go over what that pH indicator is. So they used something called phenolphthalein. Again, this is liquid. When it's basic, it's pink. And when it's acidic or neutral, it's white, or clear, sorry. So let's talk about what acid and base means. So if I am acidic, I have lots of H plus in solution. If I have basic, I have lots of OH minus in solution. This typically has low pHs. This typically has high pHs. We'll get into the pH scale later, but what I want you to kind of focus on here is the amount of stuff. So here you're looking for OH, here you're looking for H. Now remember, in the solution here, we should just see so he's gonna pour, so this is gonna show you that this is gonna be a base, right? So there's the NaOH in here. Okay. So here there's extra NaOH. This wasn't the best video, but what I would like you to write down, essentially, so here he added a little bit too much base because you can see that it's pink, it should have stayed neutral. So for this, we could just say that it remains colorless, right? And there should have been some slight heat generation. Apologize for the subpar video there. So here are just some notes on acids and bases. And so you want to say that it remained colorless, right? So the pink there is just the pH indicator. It's not actually a color change. So let's go ahead and write out our balanced chemical equation. So this is going to be NaOH aqueous plus HCl aqueous. We know that neutralization reactions are always going to make water and a salt, right? So this is water and a salt being the ionic compound. So we just have to form Na plus and Cl minus. So this is just going to be NaCl here. And since we know nothing happened, neutralization reactions will always give off heat, but we know that there was no solid formation. So that's why we're okay with just a liquid here. So for the total ionic, and to make sure it's balanced, it's a 1-to-1 to everywhere. So this is just going to be Na plus aqueous plus OH minus aqueous plus H plus aqueous plus Cl minus aqueous goes to H2O liquid plus Na plus aqueous plus Cl minus. And then if we're going to write the total, or the net from the total, this is just going to be H plus, H plus aqueous plus OH minus aqueous gives you H2O liquid. So our fifth reaction is barium chloride and high sulfuric acid. So this is not a base. BaCl2 is not a base, so this is just adding an ionic compound to acid. So let's go ahead and watch this reaction. So here we have in the solution, right, so they're using this glass rod, which has, a hole, it's a tube, so they're kind of putting it in this way so they're not splashing, so they're adding the H2SO4 into the solution of barium chloride. So let's kind of watch this again from the start. So there's the tube that's bringing in the acid. Again, it's just a safer way to add things together. So here we can see a nice cloudy white precipitate. So we'll go ahead and write that down. And I'm abbreviating precipitate as PPT. So we need to write the balanced conventional equations. This is going to be BaCl2 aqueous plus H2SO4 aqueous. Again, I'm highlighting the new pairs that I'm making, right? You can remember it any way you want. You can, there's a couple different mnemonic devices. So we have Ba 2 plus, SO4, 2 minus, and I have H plus, and I have Cl minus. Remember again, this 2, I'm not bringing over. It's not part of a polyatomic ion. I will take care of it with balancing. So this is just a 1-to-1. So this used to be Ba2, SO4, 2, but we can go ahead and cancel these 2. You don't want to mess with this 4 here. oops, sorry, I meant to highlight that. You don't want to mess with that 4 there. That 4 is like the H at the end of my name. You want to leave that on. So this is just going to be HCl. So here's BaSO4 and then HCl. So here I just need to go ahead and balance it. We're going to put a 2 there. I'm going to use the polyatomic ion way. So there's 1 sulfate, 1 barium, 1 barium. There just needs to be 2 chlorines and 2 hydrogens. So I'll just put a 2 here. Generally, I know that this is a strong acid, so this will always be aqueous, and sulfates are generally insoluble, even if they're, especially when they're with barium. So to write the total, I'm just going to write Ba2 plus 2 Cl minus. Remember again that this 2 just comes out here, whereas this 2 is going to go to both of them. Okay, same thing for this 2 for the hydrogen. So plus 2 H plus, aqueous, SO4, 2 minus, aqueous, goes to BaSO4, solid, plus 2 H plus, aqueous, plus 2 Cl minus, aqueous. Remember again, it doesn't matter the order of the compound, so you can write the Ba and the Cl after here, right? But the order of the compounds within, right? So you have to write a cation and then anion. So the net ionic, after we go ahead and cross these off, this is just going to be Ba2 plus, aqueous, plus SO4, 2 minus, aqueous, goes to BaSO4, solid. So our next reaction is going to be ammonia gas and sulfuric acid. So let's go ahead and write down our observations here. So here you can see in this video, there's a thermometer that's basically showing you kind of what's happening here. The thermometer is put in place here, similar to how the balloon in the previous video was to show you that we collect gas. The thermometer here is to show you that there's heat production. So there's heat, there's also bubbles. Remember, ammonia is a gas, so they have to kind of bubble this in. That's why it's kind of in a weird apparatus here. So there's heat, there's some bubbles. So this one's a weird one. So it's definitely why I want to go over this. So here, we can write that there's NH3, which is a gas, but technically in ours, we can make it aqueous. So in our lab, it would have been aqueous, so we'll go ahead and write aqueous here, plus H2SO4. All of our solutions would have been aqueous except for one of them, which I'll go over later. This would have been something different. So here, this is a weak base. And what that means is that it's going to grab a hydrogen. So this is kind of an exception, right? So this is a purely covalent compound, right? So it's actually going to form something strange. So it's actually going to form ammonia and then sulfate. Because ammonium has a +1 and sulfate has a -2, when you do this, that's how you get this. And therefore, this is also aqueous. It's kind of a weird one. And then I just need to make sure it's balanced. So I'm going to put a 2 here. And that should be good. So I'll have 2 NH3 aqueous. This is the total. That's not going to split up. Remember, it's a covalent compound. 2H plus aqueous plus SO4, 2 minus aqueous. Should be up by the 2. Goes to 2 NH4 plus aqueous. Almost thought I had it on the same line. And then just plus the SO4, 2 minus aqueous. So our net ionic is just going to be 2 NH3, because we see that there's the, we see that there's the sulfate on the other side. So this is 2 NH3 aqueous plus 2 H plus aqueous goes to 2 NH4 plus aqueous. I want you guys to notice that, and I'll draw it in a different color here, that there's 2's. So remember, you always want to go ahead and reduce here. So this is just going to be 2 NH3 aqueous plus H plus aqueous goes to NH4 aqueous. Remember, what's actually happening here is in the net ionic. So the next reaction, number 7, is copper sulfate and zinc nitrate. So let's go ahead and write down our observations for that. So here you can see 2 test tubes. Copper is usually blue. So there's no reaction here. So again, remember that copper 2 sulfate, I know it's a 2 because that SO4 carries a -2 charge, so there's no reaction. So remember that SO4 has a -2, therefore there's only 1 copper, therefore it has to have a +2 charge. So let's go ahead and write out our balanced molecular equation. So for here, this is just going to be copper 2 sulfate, aqueous, plus zinc nitrate, aqueous. We're gonna swap partners, so SO4 and ZN. We've got our NO3 and our Cu, and I'll just predict the products down here. So Cu is now gonna go with NO3 minus. Remember, I'm not bringing that 2 over. I will take care of that with balancing. I'm just bringing over the ions themselves. So this just becomes CuNO3 2 aqueous plus zinc sulfate. So now I just need to make sure it's balanced. And really the only thing that's not a 1-to-1, or that looks like it's in more than one, is the nitrate, but it's actually balanced because they're found 2 on either side. So our total ionic, unfortunately, we have to separate out everything. So this is just going to be Cu2 plus aqueous plus SO4 2 minus aqueous plus zinc 2 plus aqueous plus 2 NO3 minus aqueous goes to, again, I'm writing it below just because I'm running out of room. Aqueous plus 2 NO3 minus aqueous plus zinc 2 plus aqueous plus SO4 2 minus aqueous. And our net reaction is just going to go ahead and be no reaction. Our net ionic, you can just write no reaction or NR. So we'll go ahead and watch a reaction between the sodium carbonate and our calcium 2 chloride. So let's bring up this video. So this video is going to show you, there's going to be a scale here. This is traditionally how they're going to show double displacement reactions. So you can see that one container is going to have our sodium carbonate, the other one's going to have our calcium chloride. And they're going to pour one clear solution into the other. And here we can see a white precipitate. So we'll go ahead and write that down for our observations. So let's go ahead and write out our conventional. So this will be Na2CO3 aqueous plus CaCl2 aqueous. Step 1, we have to swap and crisscross, remember. Step 2, we have to balance. And step 3, we have to predict phases. I've been doing this all along, I just kind of want to remind everybody again. So remember, my Na is going to go with a new anion, and my calcium is going to go with a new anion as well. So we'll have Na plus, Cl minus, and then we'll have Ca2 plus and CO3 2 minus. Remember, this 2, I'm not bringing over with sodium. I can take care of that with balancing. I am going to bring over the 3 in CO3 because that's the actual name of this. So this is just going to go to NaCl plus CaCO3. I know that Na is soluble with everything, so that should be an AQ. And this should be the solid. I just need to balance this. I see that there's 1 CO3 on the left, 1 CO3 on the right. I see there's 1 Ca, 1 Ca. However, I see 2 chlorines and 2 sodiums, so I'll just put a 2 here. I'm going to go ahead and write out our total ionic. Remember, we have to split up all aqueous. This is to be 2 Na plus aqueous. Remember that 2 comes out. This 2 goes to both. This chlorine will come out just in front of the chlorine. Plus CO3, 2 minus, aqueous, plus Ca2 plus, aqueous, plus 2 Cl minus. Aqueous goes 2 Na plus, aqueous plus 2 Cl minus, aqueous plus CaCO3, solid. Crossing off our spectators, we see that it's just Na and Cl. So our net is going to be Ca2 plus, aqueous plus CO3, 2 minus, aqueous goes to CaCO3, solid. So the next reaction we'll do is copper 2 sulfate with ammonium chloride. So let's go ahead and watch this video. So it's a no reaction there. So we're going to go ahead and write out no reaction. Hopefully this will give your hand a break. So this is CuSO4, aqueous plus NH4Cl. Aqueous goes 2. Remember, first we have to swap and crisscross. So I'm just highlighting my new pairs here. So 1, swap, and crisscross. 2 is balance. And 3 is predict the phases. So here I'm going to have copper with a 2 plus, Cl with a minus, and I'll have NH4 with a plus and SO4 with a 2 minus. Remember, I'm not worrying about how much there are here. I will take care of that with balancing. So this is CuCl2 plus NH4 to SO4. This I know will be the solid. Chlorines are generally insoluble. Oh, sorry, they're both aqueous. I apologize. This is aqueous. Chlorides are generally soluble except for when they're with heavy metals, Ag, Hg, and lead. So it's aqueous, and then NH4 doesn't have any exceptions. So we'll write out the total. So it's splitting up all the aqueous solutions. So Cu2 plus, aqueous plus SO4, 2 minus, aqueous. And I should have balanced this. I apologize. I didn't listen to my second one. So there's 2 chlorines on the right. There's only 1 on the left. So I need to put a 2 here. There's 2 ammoniums on the right. Now there's 2 ammoniums on the left. That's why I make a checkoff list. So plus 2 NH4 plus aqueous plus 2 Cl minus aqueous. Remember that 2 distributes to both. Goes 2 to, sorry, goes to Cu2 plus aqueous plus 2 Cl minus aqueous plus 2 NH4 plus aqueous plus SO4 2 minus aqueous. Our net, you can just write no reaction, or NR. So remember, we are going to be, I'm not sure actually if you were able to see that in the last video, but I will upload my notes. So here, I think I might be having some issues with technology. Just give me 1 second. And we're back. So we're going to do sodium hydroxide and nitric acid. So hopefully that you recognize that these are, this is going to be a neutralization reaction. So this will be a strong acid and strong base. So let's watch the video. All right. So we know that we were expecting a neutralization reaction. So we're glad that we saw the heat there. So we know for neutralization reactions, we're always going to form water and the salt. So in this situation, it's just going to be Na and NO3. We'll crisscross this, that just becomes NaNO3. I see this is already a 1-to-1. Because I know no solid formed, this has to be aqueous. So let's go ahead and write out our total ionic. So this will be, I'm missing the aqueous here. So this is going to be Na plus, aqueous plus OH minus, aqueous plus H plus, aqueous plus NO3 minus, aqueous goes to, can't split up water because it's a liquid, plus Na plus, aqueous, NO3 minus, aqueous. Then let's go ahead and write out our net. This is our total. So it's going to be OH minus, aqueous plus H plus, aqueous gives you H2O liquid. All right, so our last one, just to make note again, it doesn't matter what order the OH and H are in. Remember the aqueous compounds, you can write the compounds in any order, but just remember again, for a specific compound, the covalent has to be first. So the next one we're gonna do is we're gonna do iron 3 chloride. So I know this is iron 3 chloride because I have 3 chlorines here, and I see ammonia. Now in this situation, I know, again, they're gonna bubble it in because ammonia is a gas, but for us, we know that it's a aqueous. So we're looking for Fe Cl3 plus NH3. In our last example, we saw that hydrogen, or NH3 pulled off a hydrogen, but that's not really, can't really see that here. So here they're gonna bubble in the ammonia gas, and you can kind of start seeing it by the liquid rising. So you see that color change. Let's watch that one more time. So you can see here, it used to be that nice yellow color, and then it's kind of turning this orangish brown. It should be like a rusty color. So we'll go ahead and write that down under our observations. This is another exception. So that's why I'd like to go over this. So here, like a rusty orange brown. We know that to write out the molecular equation, it's going to be FeCl3 aqueous plus NH3 aqueous goes to. Now here, what has to happen is that you have to basically make this an ion in order for it to react. So you have to make the ammonia an ion. So in the background, you have to actually react NH3 and H2O. And we know that this is going to make, for us, NH4OH. So now we have FeCl3 aqueous plus NH4OH aqueous. Now we can do our double displacement. So I just want to write this is kind of an exception. The only reason we didn't have to do this before is because the ammonia was able to rip off an H and go from there. You can do this process similarly with the other one as well. So remember now we're gonna crisscross and swap. So this is gonna be Fe3 plus and OH minus. This is gonna be NH4 plus and Cl minus. So crissing and crossing. So we know here this is going to be FeOH3. This is going to be NH4Cl. So we know here that this is going to be the solid that we form. However, we have to do one more step before we can write out our total ionic. We have to put this back into NH3 and water. And it's really important that we do that. And so let's just go ahead and try and balance this. So this needs to be a 3 over here, making it that this needs to be a 3 here. So the final balanced chemical equation will be, so it'll be FeCl3 aqueous plus 3 NH3 aqueous plus 3 H2O liquid goes to FeOH3 solid plus 3 ammonium chloride aqueous. So just take a second and make sure you have this all written down with all the different phases, and then we'll move on to the total ionic. So remember, for the total ionic, we have to split up everything that's aqueous. We can't split up water. We had originally had this as our 3NH4OH, but remember that we have to put it back into what was being added into solution. And then to do our net ionic, so remember, this is the piece that was NH4OH, and then to do the net ionic, you can go ahead and pause the video and make sure that your answer matches mine. And we have one more reaction to go. All right, so we have our last reaction, sodium sulfite with hydrochloric acid. Remember, this is sulfite, SO3, not sulfate. Let's look at our last reaction. All right. So our observations was odor, gas, and bubbles. And you'll see why there was an odor in just a second. So again, we're going to swap and crisscross, right? So I'll get into my color for our balanced chemical equation. So this is going to be Na plus is now going to be with Cl minus, and we've got H plus is now going to go with SO3 2 minus. This is going to be NaCl. Remember again, this 2 does not get carried over. So this is going to be H2SO3. So here, this is NaCl plus H2SO3. This is another and final exception. So remember, here's the other gas that we had talked about. So we have our H2SO3, which is going to immediately decompose into H2O liquid and SO2 gas. And so this is that smelly odor that the person in the video was talking about. So we can go ahead and balance this and then just carry over the coefficients if needed. So I see 2 Na, so I need a 2 here. I see 2 chlorines, that's now balanced over there. I need my SO3s. So we know that if we were to, this is, you know, if you have this balance, this reaction balance before you decompose it, then it will be okay. So let's go ahead and rewrite this. This is going to be Na2. So I'm having a little bit of technical difficulty, so I'll just leave my screen up for a second so you guys can see what I was talking about. So H2SO3 is going to immediately decompose into H2O and SO2. All right, so you can see the balanced conventional total molecular equation here. So I'm gonna, you guys can pause the video and try to write out the total ionic and net ionic, and I will show you the answer. So go ahead and pause it now and try to write it out and then check your work. All right, so now it's time for us to check our work. So here's the, here are the answers. So we've got our total and our net ionic here. So this is the end of the data portion. So go ahead and try the post-lab questions. If you guys have any questions, go ahead and send me an email. All right, thanks.